All right, in this example, I'm going to do Coletta 936, which is about a student who sits on a swivel seat. Initially, the student is at rest and holding a bicycle wheel that has angular velocity of 10.0 radians per second. The student turns the spinning wheel upside down, reversing the direction of the angular velocity. And this is a lot like the demo I did in class where I was sitting on the swivel seat and turned the bicycle wheel upside down. So I'm going to start spinning, and what we'd like to do is find the student's final angular velocity, and we know the moments of inertia of the wheel and the student. All right, see how far you can get in your, go ahead and pause and see how far you can get in your analysis and planning. I always like to start my analysis and planning with a picture. And here I'm thinking of a top view. This is the student and this is the bicycle tire. And we have the start and end time. So at the start, the student isn't moving, but the bicycle wheel is rotating, and we know its angular velocity and its moment of inertia. And here we have the student's angular velocity is 0 because they're not spinning. And we know that their moment of inertia. Right, so one of the critical things with these angular things is just sorting through all the variables and realizing that angular velocity is omega and moment of inertia is I, and all of these have little i's on them because they're initial, right? And B is for bicycle tire and S is for student. Okay, and at the end we have a different situation. We know that the bicycle tire is spinning the opposite direction, so it was going counterclockwise, now it's going clockwise, so it has negative 10 radians per second as its angular velocity. Its moment of inertia hasn't changed. Now, this is something to be careful of that you didn't have to think so much about before. So say, this isn't a particularly good example, but say the ice skater spinning who brings her arms in, that's a conservation of angular momentum where the I changes between. So you want to be careful that you think of the initial I and the final I, the initial moment of inertia and the final moment of inertia separately. So I've written them here, and in this problem, the bicycle wheel is not changing shape, nothing is walking in or out, so that moment of inertia is the same before and after. Similarly, the student has the same moment of inertia before and after, but what changes is that they might start spinning, right? So if I wanted to tell myself the story of what's going on is when the student flips over the bicycle tire in order to conserve angular momentum, they have to start spinning, and they have to start spinning in the direction of this original bicycle tire so that their angular momentum plus the negative angular momentum of the bicycle tire is the same as the initial angular momentum of just the bicycle tire. Since the person's so much bigger than the bicycle tire, I think they're going to be going slower than this 10 radians per second, but they're definitely going to be going in the counterclockwise direction because they need to be providing more positive angular momentum to offset this negative angular momentum and end up with whatever we had here. All right, so that's my plan. Conservation of angular momentum. The total angular momentum of the person in the bicycle tire before is equal to the total angular momentum of the person in the bicycle tire after. Now, before using conservation of angular momentum, I do want to check that this is an isolated system that I'm thinking about the student and the bicycle tire, and the chair, I suppose, is part of the student's moment of inertia. And so what happens is that's why we use these special swivel seats, because they have very low friction and apply basically no net torque to the system. Of course, it's an approximation. Eventually, the whole system would slow down because there is a little torque, but we'll estimate that the external torque is mostly 0, and so it's only the force of the tire on the student and the student on the tire, and that's exactly when we would have conservation of angular momentum. So go ahead and see if you can do the execution here and get to the goal, the student's final angular velocity. All right, so I started from here, and then I wrote out the angular momentum of the system before, which is the angular momentum of the bike tire times the angular momentum of the student. And then after, I similarly have the angular momentum of the bike tire and the angular momentum of the student. These are the final values. Then this is 0 because the student initially has no angular momentum because they have no angular velocity. And so from there, I did some algebra. I subtracted this over onto this side to get to this step. I divided both sides by this moment of inertia final to get here. So here I now have a formula for the final angular velocity of the student. That's our goal. And I just plugged in all the numbers here. And you'll notice that I ended up with a positive number because I had this minus a negative. And it's 2.4 radians per second, or since we have 3 sig figs, 2.40 radians per second, which as I expected is a positive, right? It's this counterclockwise direction. and less than the 10 radians per second because the person is so heavy compared to the bicycle tire. And this is a lot like what happened in class when I did the demo. When I turned the bike tire over, I started spinning, but slowly compared to how fast the bike tire was spinning. So this does seem to make sense to me. And then I think we're done with this conservation of momentum example.